We carry on with the program. Next is Abhinav Bhaskar. He's from the University of Stavanger. He was working at the University of Stavanger. He's done research into techno-economic evaluation of hydrogen-based steelmaking. Abhinav, may I give the floor to you?
Thank you so much. I hope you can hear me.
Yes, we will definitely try. I think
Okay. Okay, cool. Just a confirmation. Can you see my screen now?
Yes.
Okay. Okay.
Could you move to presenter mode to increase the size of the screen, perhaps?
Oh, display settings. Does that work?
Yeah.
Okay.
Thanks.
Perfect. Thanks for the introduction, Doug. I would be talking about my third paper and the final paper, and this is regarding the decarbonization of primary steel production, which we heard quite a bit about yesterday, and how the techno-economics would play out if we had a plant, a green hydrogen-based steel production plant in Norway. So before going into those details, I would just mention the strategies which could be used for decarbonizing the steel sector. The steel sector and other industries are considered hard to abate sectors where direct electrification is not possible in most cases. As we saw yesterday as well, that coal is the primary source of energy as well as used as a chemical feedstock. So there we could use two strategies. We could use demand side strategies to reduce demand of primary steel or steel in general by using material efficiency, using less material, recycling, or through material substitution. Like in the construction sector, there's a lot of talk about substituting steel with wood, for example. But apart from that, we also have measures on the supply or the production side where we could change the technology itself to reduce the emissions from the production processes where hydrogen-based direct reduction has been talked about quite a bit. There's an alternative of using CCS or CCUS, and also the injection of biomass directly in the blast furnaces. And one of the upcoming technologies I would say is electrolysis, where electricity can be directly used. And here also the emissions would be quite low, but this is at quite a low TRL. Just a comment on this for the demand strategies, there is a lot of discussion about these measures, but the demand for steel is going to increase because it's directly related to the population growth, and the demand would probably come more from the developing countries where the infrastructure is still to be built, and steel would be used more and more. And it's projected that the demand for steel would increase by more than 50% by 2050. So we need measures on the production side. So one of those is the use of hydrogen instead of carbon for the reduction. And I'm showing a system which could do the same for the, I would say for time purposes, I would not go detail into each of the components, but I can get quickly on the shaft furnace, which is a replacement of the blast furnace, which is traditionally being used for steel production. And here, instead of coal, you can use hydrogen as a reducing agent, which produces iron, pure iron at a temperature of 700 degrees Celsius, which can be fed to an electric arc furnace along with scrap, or we can do 100% DRI as well, and that could produce steel. So what is the energy consumption for such a system? It's close to 4 megawatt hour per ton of liquid steel, which is slightly higher than the BF, BOF, or the blast furnace based steel, which we've traditionally been using. And majority of the energy is consumed for producing hydrogen. And this is more than 75, almost 75% of the total energy is consumed by the hydrogen production step. But the emissions of this system can be divided into direct emissions and indirect emissions. And the direct emission ranges, as I'm showing in this panel here, are quite low. And the indirect emissions are based on the consumption of electricity for the production of hydrogen. And here I'm pointing out some of the countries where the emissions will be extremely low because of the low emission factor of the electricity. And a point to mention here, in Sweden, there's already a demonstration plant running for hydrogen-based steels in August 2020. And new projects have been announced in various countries, including Spain and Germany. When I started my PhD, there was hardly any. And now I think we have a list of at least 30 projects coming up all across the world with hydrogen-based steel making. We did a NPV sensitivity analysis to analyze what are the main factors which affect the financial feasibility of the plant, and we found that electricity costs are the major factor which affect the feasibility. And we also did a global sensitivity analysis and got more or less the same result there, where the price of electricity was the major contributing factor. So based on these findings, we started thinking about the use of or the relocation of iron and steel industries to countries with cheaper electricity prices. And Norway was one of the choices, which is quite close to the EU demand centers and has one of the cheapest electricity prices as well. So here I'm showing the configuration where the electricity can be either purchased from the electricity markets, from the day-ahead markets, or we could sign long-term power purchase agreements. So here we have analyzed the use of electricity from electricity markets by looking at the use of hydrogen production with a storage to leverage the price variability in the day-ahead electricity markets. And the reason why we chose Norway was because of the access to cheap electricity, and because of which a large amount of aluminium producers have set up their plants in Norway. And also, there is a huge demand for low carbon steel in Europe, and Norway is quite close to this region. And also, one of the contributing factors was the huge offshore wind potential in Norway, which would be developed in the future. It's almost close to 12,000 terawatt hour per year, but most of it is in deep water, which would need floating resources. Um, to analyze this problem, we developed an optimization framework based on Python, and we used Pyomo, open source library, for developing this problem. And the objective function was to reduce the total cost of production of hydrogen. And it was a simple function where the cost vector here is the cost of electricity price per hour. And we use different electrolyzer capacities to analyze how the cost would vary. We got some interesting results. Here I'm showing the production pattern for different electrolyzer capacities and also the storage status for different electrolyzer capacities here. And these are, I would say, this is a histogram where I'm showing the frequency of hours for which you would produce a certain amount of hydrogen. So here you can see that the number of hours at which the electrolyzers remain idle increases as we increase the capacity. And this could also indicate that the steel plant can participate in capacity markets or demand response markets as well when it's available. This is the electricity price for different configuration, and this is the hourly price variation. It does not give very I would say indicative results, but when we do it for aggregated for an hour for a day, it becomes clear that when we increase the capacity, the electricity cost of production reduces significantly. And similarly for a monthly and yearly version as well. So for the annual, if you see the annual variation in total electricity cost of hydrogen production, it reduces significantly as we increase the electrolyzer capacity. But the levelized cost of production increases as we increase the capacity of the electrolyzers. This is related to the fact that electrolyzers are still very costly. And when we increase the electrolyzer capacity, we also have to increase the storage sizes. So those both are connected to each other, and that leads to an increase. But the levelized cost of production for steel, if we purchase electricity from the grid or the day-ahead market, it's substantially lower compared to if we have a corporate power purchase agreements. And here the range is almost $594 per ton, which is comparable to, I would say it's 20% higher than the levelized cost of production from baseline technologies. But with some of the companies like BMW and Mercedes and also Volvo showing interest in buying green steel by also paying a premium, this could be a reasonable cost in the future. So last slide on the conclusions. The levelized cost of production varies from almost 584 to 989 for different configuration. And participating in the electricity markets reduces the production cost by 8% compared to a plant with similar capacity if they buy fixed electricity prices. And the increasing the electrolyzer capacity reduced the operational cost. However, the fluctuations were not high enough in Norway to justify the additional electrolyzer and hydrogen storage capacity. And we also saw that if we have access to underground hydrogen storage, where the storage costs are much lower, and if you increase the capacity of storage, then it is possible to decrease the operational costs further. And that would be our, I would say, future research work. So with this, I'll end my presentation. Thank you for your time.
Thank you, Abhinav. Very relevant and also a very actual topic, especially also here in the Netherlands. So thank you for these insights.